can't buy a chip that holds less data. So it might not even be using 128-bit. The part of the problem too is you want your batteries to last a long time. You don't want your consumer to say, oh, the battery only lasts a week or 2 weeks because they're transmitting too much data. So when we're developing protocols, we want to transmit as little data as possible. They turn the transmit chips off when they're not sending data. So if you can, instead of sending a very long hash, a very long serial number, they're going to try to do it as least amount as possible, and it's limited by how many devices you want to not clash with. When we look at one of the devices, it'll say maybe it has 65,000 unique codes, which is it's a 16-bit serial number. So for the purpose of this talk and for the demonstration, I chose one of the devices to go through entirely, and this is going to be the Kensington Pocket Presenter. I chose this device because it's end of life, so hopefully not too many people get owned through this or the presentation's messed up. And by using an old device, if you guys want to try this, there's plenty of new devices, and go ahead and try a new one. Let me know how it goes. So this is the advertising talk here where it says you can transmit 50 feet away. All the information here pretty much highlights ease of use. It's lightweight. It's intuitive. It has a built-in laser pointer. No extra software. No drivers. 65,000 separate IDs. That's a lot, right? 16-bit, that's huge. And of course it works with Keynote because, we need Macs to be able to do their presentations as well. And actually for our demo, we'll be testing against a Mac. So this is some software that runs on Win32 computers. What it does is it hooks the USB stack, and when it sees a hid device, it's going to tell you the vendor ID, product number, and most importantly, at the bottom where it says collections, you're going to see generic desktop keyboard application. So it's identifying itself as a keyboard. So the first thing you do when you buy one of these devices, you look for the FCC ID. When any company in the United States is going to sell anything that transmits over the airwaves, they need to fill out an FCC application. They'll receive an ID if it gets approved. Part of the application process is submitting schematics, block diagrams, testing, pictures, external and internal pictures, and also where the labels go. They want to know where you're going to put the label. The label is very important to them. So the FCC provides this great website where you just type in the FCC ID. It's going to show you the application and all the files that they included as part of the application. There is an option when you're applying for an FCC ID to declare some of the data as confidential. And in this case, which is why I'm using this one as an example, Kensington did not apply for confidentiality on their schematic. So we're going to have part numbers that are standard parts, no custom parts. We have a schematic, and there's the schematic. This is for the receiver side. It has in the kind of center area, we have the three main chips that we saw on the dongle, all the way to the far side. That's the connector for USB, and on the left, I don't know what that is. That's probably something to cut down noise or something like that. It doesn't matter. There's no logic there. We're not really interested in it. And this is the logic for the transmitter. If you're not too familiar with schematics, just to go through it a little bit, obviously the yellowish rectangles, those are chips. If you go down towards me from the chip, you're going to see switches. So those are the switches on the presenter, which is sending input into that microcontroller. And to all the way at the end, the little chip, that's going to be that's the EEPROM that most likely holds the serial number, so that the microcontroller can read the serial number and put its packets together and send them out over the wire. And we also have towards the bottom, we have our transmitter chip. So now we can start reversing. We got all the easy data that we could get, and now we have to see what is in what is this device doing, how the protocol works. So we know that we have one-way traffic by looking at the data sheets of the chips, because they only transmit, it doesn't receive, or it only receives and doesn't transmit. Keyboards are the exception. Keyboards need to have two-way communication so you can light up the caps locks key, or the caps locks light, and things like that. These do not have standard protocols. Every manufacturer is making their own. That being said, there's probably only 3 or 4 of these that are really popular. So you'd only have to go through 3 or 4 to pretty much cover all the presenters. As far as wireless mice, I'm thinking that top 2 vendors are Microsoft and Logitech, and they're going to probably keep their data protocol the same throughout. We have varied frequencies, so we have, as mentioned before, we have ranges from 27 to 900, 2.4. Like the Microsoft keyboards, most of them are 27 megahertz. The device that we're going to be demoing, or I'm going to be demoing, is 900 megahertz, and some of them are going to be 2.4. So we're going to take a look at the receiver. This is the data sheet for the microcontroller. Publicly available data sheet is going to have all the pinouts. It's going to match to the schematic. You're going to be able to figure out certain types of modes by what some of the pins are tied high or tied low, if there's different modes. And you probably won't be able to dump the data from the microcontroller. These devices are usually one-time programmable, and they blow a fuse. There are ways to take off the layers, the coating, the plastic coating that's on the outside, and try to get into the chip, but it's going to be a waste of time. That's too much time. We'll be able to figure out the protocol and what it's doing without doing any of that work. And here is the data sheet for the receiver chip. And we take a look at the transmitter, and there's that's the receiver. And this is this is part of the transmitter data sheet. The best part of this data sheet is that second line. Applications, car alarm and home security systems. So people are using this in car alarms and home security systems, and it can only transmit, it can't receive. It can't authenticate. You can do replay attacks. And this is protecting someone's house, someone's car. I mean, if someone is looking at your I don't know, $20, $30 wireless presenter, that's fine. If you're spending thousands and thousands of dollars on a home security system, or hundreds of dollars on a car security system, I hope it's better than this. I hope they're not using this chipset in your car alarm. I'm sure someone hopes that they are, though. So here's a block diagram. In the middle, we have MCU is just shorthand for microcontroller. Up at the top, we have our EEPROM, which is going to hold our serial number authentication data. Our inputs, that's just a box that represents all the switches or buttons on the device. Doesn't really matter what the input is. It's going into the microcontroller. And then we're sending it to the transmitter chip. And the transmitter chip sends it up that piece of solder that represents an antenna. And there's the data. Here's the dongle. Once again, we have a microcontroller that also speaks USB. It has the EEPROM for the authentication. And there it has the USB port and the receiver chip. And the microcontroller is going to receive a bit pattern, just like the transmitter chip is going to receive a bit pattern, because the these are digital chips. They're not analog. They're not going to send data out that is modulated. That's what the transmitter chip is for. So we'll be able to look at that in an oscilloscope, in a logic analyzer, or what have you, and we use that data to try to reverse the protocol. So if it's one-way data, one-way messages, it has to have the authentication data so that different devices don't get confused and talk to each other. So every packet has to have authentication data, and every packet has to have the data it wants the device to process. So in order to start tapping and looking at this, we want to tap right before the transmitter chip. We don't want to start tapping at the receiver because there could be noise, there could be error correction that's done by the microcontroller on the other end. So we want the cleanest signal possible. So we look at the input to the transmitter chip. After we figured out the protocol, we verify on the receiver end to make sure that we have the protocol right. Because at the receiver end is where we're going to want to make a universal sniffer. So no matter what type of authentication data is coming through, we'll be able to listen to all the messages. Basically, like sniffing promiscuous mode on Ethernet. So here's the device that is coming off of the microcontroller. It's just tack soldered on there, little thin piece of wire. It's like 30 gauge. You just barely hold it on there and just tack it on. Excuse me. A drink of champions. For the purpose of the talk, I was trying to use pretty inexpensive equipment. So someone that is looking to get started in this can see that you can use inexpensive equipment. You don't have to spend thousands of dollars. This device here, I believe, runs say that $129. And actually, this is the same device that Joe Grand, which is in the front row, uses in his class. So if any of you took his class, I'm sure you recognize this oscilloscope. And here's what we get. You'll notice that the picture looks kind of weird because the parallax scope, it sucks. It works, but it sucks. So what I had to do is cut and paste the different sections together. That's why the bottom looks very weird. It lets you scroll the data, but it only lets you take a capture of what's currently displayed inside the scope window. That's just a software issue, and I wish they would fix it because this is not so cool.
How fast can that scope sample?
Joe? Not that fast.
Yeah, I think it can do 1 million samples a second for one channel and 500,000 if you're doing two channel. It's slow. Bandwidth is like 20 or 50K. It's slow.
So the type of data that we see with these types of protocols are usually about 10K. Like the standard PS2 keyboard, those have an internal clock and those transmit about 10K. So they're probably trying to emulate kind of the same types of speeds. And we see these different sections. There's obviously some kind of delimiters going on here. There's these big chunks of lots of activity and then more sparse activity.